the Quantization Arms Race. The open-weight model community has turned VRAM optimization into a competitive sport, and the Qwen 3.6 series is the current arena. A detailed breakdown of running Qwen 3.627b at IQ4XS quantization reveals that llama.cpp commit 1 dab 5f5 of 44 hardcodes the AT&KV tensor to a Q5K minimum, inflating the model from 14.7 GB to 15.1 GB with no meaningful perplexity gain. The fix is straightforward. Patch the importance matrix to let IQ4XS apply uniformly. And the reward is 110K context on 16 GB VRAM using Turbo 3KV cache quantization. That is a 27 billion parameter model fitting entirely in a single consumer GPU's memory with a context window that rivals many API providers. Speaking of KV cache tricks, Google's TurboQuant paper generated excitement, but the community reception has been lukewarm. The technique is not officially merged into llama.cpp, and forks that implement it show marginal improvement over the existing Q40KV cache quantization that has been available for months. Several community members tested the available forks and found the memory savings negligible for the added complexity. A few hundred megabytes at best on typical workloads, which matters far less than the multi-gigabyte savings from proper weight quantization. The consensus from practitioners, overhyped for real-world use, at least in its current form. The gap between an interesting research paper and a practical llama server flag remains wide. The model leaderboard itself keeps shuffling. Updated benchmarks show Gemma 4 pulling ahead of Qwen 3.5 on several tasks, but the more interesting development is the pairing of Qwen 3.627b with Minimax M2.7 as a local coding stack via OpenCode. Users report this combination as a credible replacement for Claude Code on tasks that do not require frontier reasoning. At zero API cost. The open-weight models are no longer just catching up. They are carving out practical niches where API models cannot compete on economics. One user running Qwen 3.627b UDQ6 KXL on an RTX 5090 reports 200K context at 50 tokens per second, calling it actually usable for coding workflows with Claude Code as the interface. The Q6KXL quantization sits at a higher fidelity point than IQ4XS, but demands more VRAM. A trade-off that the 5090's 32 GB handles comfortably. The practical implication: the latest consumer hardware can now run a near full-quality 27B model, with context windows that would have required API access 6 months ago. At the extreme end of the compression spectrum, BitNet's ternary quantization architecture weights constrained to -1, 0. +1 continues to attract speculative interest. The ternary Bonsai 8B model fits in 2.2 GB, which is remarkable. That is an 8 billion parameter model in less space than a typical movie file. The appeal is obvious. Ternary weights eliminate multiply-accumulate operations in favor of simple additions and subtractions, potentially enabling inference on hardware that cannot run traditional floating-point models at all. But quality at this compression level remains the open question that proponents tend to wave past. BitNet is architecturally elegant, but until ternary models can match even Q4 quality on meaningful benchmarks, it stays in the promising research category rather than the practical tool category. AI coding agents level up. A new open-source coding agent called Dirac topped the Terminal Bench 2 leaderboard using Gemini 3 Flash Preview, scoring 65.2%, beating both Google's official baseline at 47.6% and the top closed-source agent Juni CLI at 64.3%. The technical approach is interesting: hash-anchored edits that use stable line hashes instead of fragile line numbers, AST-native manipulation for structural refactoring, and multi-file batching that processes several files in a single LLM round-trip. On 8 real-world refactoring tasks across Transformers, VS Code, and Django codebases, Dirac achieved 100% accuracy at an average cost of 18 cents per task, 64.8% cheaper than the competition. The agent is a fork of Qwen with a fundamentally reworked editing strategy. No MCP support, which is a deliberate choice, native tool calling only for reliability. The configuration management problem for coding agents gets a direct answer from Anywhere Agents, a project that provides a unified agents.md configuration format that works across Claude Code, Codex, Gemini CLI, and other agent frameworks. It includes a pack system for composable rule sets and a writing style guard that blocks roughly 45 AI tell words. The underlying problem is real. As developers run multiple agent frameworks in the same repository, maintaining separate configuration files for each becomes unsustainable. A single declarative format that all agents can read is the kind of boring infrastructure work that eventually becomes essential. Meanwhile, LaMindex released ParseBench, a benchmark that tests whether document parsing tools produce output that AI agents can actually act on. The benchmark covers roughly 2,000 human-verified pages from real enterprise documents across 5 capability dimensions: tables, charts, content faithfulness, semantic formatting, and visual grounding. Llama Parse Agentic leads the leaderboard at 84.88% overall, with Gemini 3 Flash at 75.05% and Reducto at 72.97%. The evaluation is entirely deterministic, no LLM as a judge. The most revealing dimension may be semantic formatting, which tests whether parsers preserve meaning-carrying formatting like strike-through text. A superseded price is not the current price. Most parsers fail badly here, and any agent downstream inherits that failure silently.
Industry turbulence. OpenAI released GPT-5.5, priced at $5 per million input tokens and $30 per million output tokens. The community response has been measured rather than enthusiastic. On SWE Bench Pro, GPT-5.5 scored 58.6%, trailing Anthropic's Opus 4.7 at 64.3%. The pricing positions it as a mid-tier offering, cheaper than frontier models but more expensive than the flash-tier alternatives that have been eating into API revenue. OpenAI appears to be filling out its model lineup across price points rather than pushing the frontier forward with this release. For coding-heavy workloads where SWE Bench Pro performance correlates with real productivity, the 6-point benchmark gap matters more than the price gap. In a story that writes its own punchline, Tools for Humanity, Sam Altman's identity verification company announced a partnership with Bruno Mars that turned out to be fake. The company had actually partnered with 30 Seconds to Mars and confused the two. An identity verification company that cannot verify the identity of its own partners is a comedy of errors. But it also raises a real question about the operational rigor of companies asking billions of people to scan their irises. If your verification process cannot distinguish between two musicians with Mars in their name, what confidence should users place in the rest of your identity infrastructure? The political environment around AI continues to shift. The Trump administration, which had picked a public fight with Anthropic over safety policy disagreements, appears to be backing off. The details remain thin, but the pattern is familiar. Aggressive posturing followed by quiet retreat when the economic and diplomatic implications of antagonizing a major AI company become apparent. AI policy in the current administration has been more reactive than strategic, and this reversal fits that pattern. Underneath the daily news cycle, Max Tegmark's Life 3.0 framework continues to shape how researchers think about longer-term AI trajectories. A recent editorial revisits the book's taxonomy of 12 possible AI futures, from benevolent superintelligence to civilizational extinction, and notes that surveyed AI researchers estimate roughly a 1 in 6 probability of an extinction-level outcome. Whether that number is calibrated or performative, it represents an untrivial fraction of the people building these systems, expressing deep uncertainty about where they lead. The gap between building faster and thinking harder about where we are building toward is not closing. Securing models and systems. A new paper introduces ARMS SL, a framework for embedding adversarial robust watermarks into self-supervised learning pre-trained encoders. The problem is significant. SSL encoders like SimCLR, Moco V2, BWAL, SimCM, and DNOV2 are expensive to train and easy to steal. Just fine-tune the last layers and the original weights carry over unmarked. ARMS SL uses 3 mechanisms: paired discrepancy enlargement to create detectable differences between watermarked and unwatermarked encoders, latent representation entanglement to survive fine-tuning attacks, and distribution alignment to maintain the encoder's utility on clean data. The approach is black box, meaning verification does not require access to model internals. IP protection for foundation models has been an afterthought in the rush to train and deploy. Work like this starts building the forensic infrastructure that will eventually be necessary when model theft disputes reach courtrooms. On the offensive security side, GTF opens the curated database of Unix executables that can be exploited for privilege escalation, shell escapes, and file operations. Resurfaced on Hacker News this week. The project catalogs living off the land techniques, ways attackers use legitimate system binaries awk, Python, Vim, tar, and dozens more to bypass security controls without installing malicious software. Each entry documents the specific capabilities of a given binary, whether it can read files, write files, spawn shells, or escalate privileges, along with exact command invocations. For defenders, it is an essential reference for audit and hardening. For anyone building AI agents that execute shell commands, it is a sobering reminder that the attack surface of run this bash command is vastly larger than the command itself. Every binary in path is a potential escalation vector, and the agent sandbox is only as strong as its least restricted executable. Training theory gets a new lens. A paper on generalization at the edge of stability introduces a new geometric quantity called sharpness dimension, SD, that may explain why neural networks generalize well despite operating in a regime where traditional theory predicts they should not, when the learning rate is large enough that training loss oscillates rather than monotonically decreasing. The edge of stability regime. The authors model the optimizer's trajectory as a random dynamical system on the Lost Landscape's pullback attractor. Using Lyapunov theory from dynamical systems, they prove a generalization bound that depends on the sharpness dimension of this attractor rather than on the number of model parameters. The bound is validated on MLPs, GPT-2, and grokking experiments. If the result holds up under further scrutiny, it offers a principled explanation for why overparameterized models trained with large learning rates do not simply memorize their training data. The geometry of the optimization path constrains effective capacity in ways that parameter counting misses. The mathematical foundations underlying these training dynamics continue to attract educational attention. A recent video breakdown walks through the calculus of gradient-based optimization from first principles, covering the chain rule mechanics, loss surface geometry, and the specific derivative computations that make backpropagation work. The presentation builds intuition for why gradient descent works at all, and more importantly, why it sometimes does not, by grounding abstract optimization concepts in concrete geometric reasoning. For practitioners who use these tools daily without fully understanding the mathematics beneath them, this kind of foundational content fills a gap that blog posts and API documentation leave open.
Hardware from chip to orbit. Google published the engineering details behind Torch TPU, its integration layer for running PyTorch natively on tensor processing units. The architecture is built on an eager-first philosophy with 3 execution modes. Debug eager for single-op synchronous execution, strict eager for asynchronous single-op dispatch, and fused eager, which automatically fuses streams of operations into dense computational chunks, delivering 5.0, 1.00% speedups over strict eager with no user configuration. For full graph compilation, Torch TPU routes through XLA via stable ACLO rather than Torch inductor. A deliberate choice because XLA already understands how to optimize communication computation overlap across the TPU's interchip interconnect torus topology. The MPMD support is particularly notable. Prior PyTorch/XLA only supported pure SPMD code, which meant developers had to carefully remove any rank divergent behavior, even logging. Torch TPU isolates divergent executions automatically. The 2026 roadmap includes bounded dynamism for variable sequence lengths and integration with VLLM. At the opposite end of the compute spectrum, DSPI turns the $4 Raspberry Pi Pico into a fully featured audio DSP processor. The firmware implements parametric equalization, active crossover filters, time alignment, loudness compensation, and headphone crossfeed. Capabilities that typically require dedicated hardware costing hundreds of dollars. The Pico operates as a USB sound card, receiving audio over USB and processing it in real time before output. Room correction, a feature that usually demands proprietary measurement software and expensive hardware, is implemented entirely in the Pico's dual ARM Cortex-M0 Plus cores. For the audio engineering community, this democratizes DSP processing in a way that commercial products have resisted. Apple Silicon users running 3D generation workflows now have a 3x speedup path. Hunyuan's image-to-3D texture pipeline ported to MLX runs 3 times faster than the PyTorch equivalent while using half the VRAM. The optimization leverages MLX unified memory architecture and metal compute shaders, turning what was a multi-minute generation process into something approaching interactive speed. For creative workflows that iterate rapidly on 3D asset generation, this is the difference between a tool you wait for and a tool you use. Embedded systems development is getting more interesting too. A detailed write-up demonstrates running bare metal Rust on the ESP32 S3 second core while ESP, IDF, and FreeRTOS run on the first. The approach uses a separate flash partition and MMU mapping to load the Rust binary, making it hot swappable without reflashing the FreeRTOS side. Core 0 handles Wi-Fi, Bluetooth, and OS tasks. Core 1 runs deterministic Rust code with no RTOS jitter. For robotics and real-time control applications, this dual personality architecture gives you the connectivity stack of ESP, IDF, with the timing guarantees of bare metal execution. The concept of dark factories, fully automated manufacturing facilities with minimal human presence, is starting to intersect with AI deployment in physical infrastructure. Early demonstrations of shipping AI-driven factory automation into production highlight both the potential and the integration complexity of moving from cloud-hosted models to embedded industrial control systems where latency tolerance is measured in milliseconds and failure modes involve physical machinery, not just HTTP 500 errors. From orbit, DRISHX exploits an overlooked property of Sentinel-2 satellite imagery. The 1.01 second timing offset between the satellite's RGB band captures creates spectral smear artifacts on moving vehicles.
by training a random forest classifier on a 7-feature pixel stack derived from these temporal band offsets. The system detects and counts trucks on highways without any high-resolution commercial imagery. The approach is clever. It turns what most remote sensing pipelines treat as a calibration artifact into a signal. Free 10-meter resolution satellite data, refreshed every 5 days, becomes a freight intelligence feed. For supply chain monitoring and infrastructure planning, this is surveillance-grade capability at science-grade pricing.